Yesterday we continued on with this stream of doing problems involving multi-forces, involving more than one force. And the thing that we introduced yesterday in that context was, we call them inclined plane problems. It's kind of a fancy way of saying hill problems. We have situations like this, where maybe we've got an object that's on a hill and we want to find its acceleration. Maybe there's friction in there, maybe there's not. Okay, maybe somebody's pulling it up the hill, maybe somebody's not pulling it up the hill. Bottom line is, okay, there's something on a hill on an incline with more than one force acting on it. Now we know when we look at this, there's at least two forces that act on it. Okay, we know that there's at least the force of gravity that acts down on this object. It's going to be equal to m times g. It acts straight down, always straight down, okay, regardless of what the incline is. We also know that there's going to be a normal force that acts perpendicular to the surface. Okay, it's going to act this way, 90 degrees to the surface. Now, we also know, and this is the crux of this one here, guys, we also know that this line that joins the normal force to the force of gravity, in other words, the combination of the normal force and the force of gravity, we know that that force has to be parallel to the hill. It has to be. Look, the normal force is perpendicular to the hill. The force that pulls it down the hill, that we're calling it FH, is the combination of the normal force and the force of gravity. So if the force that pulls it down the hill is parallel to the hill, and the normal force is perpendicular to the hill, then FH and FN must be 90 degrees to each other every single time. Now I'm drawing FH up here in a separate spot. Does that mean there's two FHs? Not at all. There's one FH, one force of the hill, sometimes we call it F parallel, that's pulling it down the hill. It is the combined normal force and force of gravity. I've just chosen to draw it right here, first of all, because it's easier for me to calculate there. And I've chosen to draw it up here, second of all, because it's easier for me to see what effect that has on the problem, what effect that has on the object. Okay, does that make sense? Now, we may have a force of friction that pulls it up the hill. We may have a guy pulling it up the hill. Whatever, that's something altogether different, okay? What we're concerned about right now is just this FH, okay, the force that pulls it down the hill. So how would we deal with this once we've found that FH? We just set it up the same way as we set up the rest of them. We'd say the net force is equal to the sum of the forces. FH plus whatever other forces we have acting there, force of friction plus the applied force, whatever other forces we have acting. Is it easy enough? Well, we've drawn a diagram to get FH. How do we actually find the value of FH there? We're always going to know what that angle is, okay? Let's say it's 30 degrees right here. We're always going to know that this one's going to be 30 degrees as well. Okay, whatever the angle of the hill is going to be the angle between Fn and mg. If we know that angle, then how do we find the value of FH there? It's a little bit of trigonometry, right? We know this. We want to find the opposite side of the triangle, FH. Okay, we have the hypotenuse, m times g, or at least we can find that by multiplying mass times 9.81. Let's say sine 30 degrees is equal to opposite over hypotenuse. Okay, whatever m times g is. Solve for FH. Okay, again, once we have that value, we go up here, we do our thing. We had two homework questions on this last night. Page 179. I suspect that we didn't get completely through both of those questions without any issues. Is there anybody that needs number one gone over? Anybody that was here that needs number one gone over? Kid, were you here yesterday? I can't remember. No? Anybody for number two? Okay, we're going to go over number two. Okay, and hopefully that'll help people that weren't here. If it's not enough, then come and see me and I'll help you with it individually, okay? Let's look at number two. It says a 55 kilogram skier is accelerating down a 35-degree slope. So here's my slope of 35.0 degrees. Here's my 55 kilogram skier. The skier's acceleration is 4.41 meters per second squared. We want to find the force of friction, the force of kinetic friction, sliding friction between the snowy surface and the skis. All right, which way is this skier going to move? Up the hill or down the hill? That's an easy question, right? Okay, you're a skier, you don't slide up the hill, you slide down the hill. Unless you're in one of those, they have them in a few places around, one of those things that they call magnetic hills. You ever seen one of those? No? No? You ever heard of one of those? I've heard of a few of them. I've been to one of them in New Brunswick. It's called Magnetic. That's what the name of the town is called. Is Magnetic Hill. It's an optical illusion, but it's somehow set up so that it looks like and feels like when you put your car in neutral that you're actually rolling up the hill instead of down the hill. You're really going down a hill. It just feels and looks like you're going up the hill. Okay. In reality, you're always going to slide down that hill, right? So if he's moving down the hill, which way is friction going to be? If he's moving down the hill, which way is friction going to be? Up the hill, right? Friction's got to be this way. Hey, we don't know the value of the force of friction. That's what we're trying to find. Now, what other forces do we have acting here besides the force of friction? Got to be something. What's one of them? Gravity. And gravity acts which way? Straight down. So let's draw that right now, straight down. That's m times g, gravity. 55 times 9.81. What other force or forces do we have acting here? Always. Which one? The normal force. Which way does it act? To the surface? Yeah, 90 degrees to the hill. Could I draw the normal force there? Would that be okay? I could draw it there. It wouldn't help me. But it's not wrong to draw it there. Okay, I want to draw it somewhere else because I want to draw it somewhere where it's going to help me. I'm going to draw it down here. It's the same thing, right? It's pointing in the same direction, and I have it drawn the same value, the same magnitude. Just a lot more convenient right here. Okay, let's label that Fn. Let's draw this line in red right here at 90 degrees to the normal force. And what are we going to label this force, this red force? I'm going to call it FH. Okay, sometimes, I mentioned yesterday, sometimes you see it called F parallel. Same thing. FH is the combined normal force and force of gravity. That's the force that pulls it down the hill. I need that force. I need how strong that force is, the value of that force. What's the angle right there? Over 35 degrees. It's going to be the same as the angle of the hill, 35 degrees. What side of that triangle there, that blue and red triangle, are we looking for? Opposite, adjacent, or hypotenuse? What is it? Opposite, yeah. So let's say sine 35 degrees is equal to opposite, FH, over the hypotenuse. And the hypotenuse is m times g, force of gravity. That's going to be 55 times 9.81. Okay, let's get that value now. 55 times 9.81 times sine 35. 309.4732. Is that good? Anybody else have that? All right. 309.4732 newtons is the force of the hill pulling it down. Let's redraw this. Remember we said yesterday we kind of like to straighten this out? Here's the skier. Here's the force of the hill that has a value of 309.4732. And here's the force of friction. We know that F net is equal to the sum of the forces, just like we've been doing for over a week now. FH plus FF. We know that M times A is equal to the sum of the forces. The mass is 55. And A is, what's A? 4.41? I'm probably going to make it actually not 4.41, but, right? Was your hand up? Oh, you can answer the question always though, right? But it's 4.41? Okay, I'm going to make it negative. Just because I'm making left negative in my diagram. But if you make left positive in your diagram, that's okay. You just need to be consistent. So I'm going to make it neg 4.41. That means FH is neg 309.4732. Ryan, what did you make FH? Positive or negative? Okay, then you're good then, because you were consistent with your acceleration and your force of the hill. Let's solve for FF there. So we're going to say 55 times 9.81. 55 times 4.41 plus 309 gives me a force of friction here of positive 66.9 newtons. Ryan, you would have got negative 66.9 newtons, right? Okay. But for me, forward was positive, and for you, forward was negative. Does that make some sense, guys? Okay with that? All right, let's try another one. Looks a lot the same, except this time it's a loonie instead of a skier. There's friction, except, oh wait, it's static friction instead of kinetic friction. What do you know about this loonie if we're trying to find the force of static friction acting on the loonie? It isn't moving, right? It's at rest. Okay, you guys have seen this before, right? Something's on a hill, it doesn't slide down the hill. I think I mentioned to you guys the very first day we introduced friction. When I go home sometimes, okay, there's a banister leading upstairs. As soon as I go in my front door, I take my phone out of my pocket and I set it on that sloped banister. I've got the OtterBox case with the rubber on the back, and it doesn't slip. Okay, so the phone will stay there. That means that the force of the hill pulling down is less than the maximum force of static friction. In other words, static friction ends up being the same value as the force of the hill, the force of that banister. Okay, we want to find the force of static friction acting on this loonie. Do you know where to start? Well, we should. We know that friction is pulling it up the hill. Now, it's not moving up the hill, but it's not going to move down the hill either because the loonie is just sitting there. We know there's got to be a force that's acting down the hill that counters that. The force of the hill. We know that we have a force of gravity acting down. We know that we have a normal force acting perpendicular to the ground. And we know our force of the hill is the combined normal force and force of gravity. We know that's 90 degrees, and we know that angle right there is 25.0 degrees. I'm going to draw the force of the hill over here as well. Not two forces of the hill, just one, drawn in two different places. Well, the next thing we do is, well, what I like to do at least is straighten it out. We've got the force of static friction acting to the right. We've got the force of the hill acting to the left. We know the net force is equal to the sum of the forces FH plus FSF. Hey, quick question. I asked this yesterday, but I'll ask it again. Why are we not including the normal force and the force of gravity in this diagram right here? They don't cancel each other out. Okay, they cancel out when one is like this and one is like this. I got gravity straight down and I got normal force at some other angle. Why am I not including those two forces in this diagram right here? There's a simple, quick answer to that question. Yep. Yeah, I am including them. I'm not ignoring them. I am including them. FH is not a force that acts really on its own. FH is the combination of the normal force and the force of gravity. So by putting FH in there, I am taking into account those two forces. Does that make sense? Tom, does that make sense? All right. Net force is also equal to what? Besides the sum of the forces? M times Acceleration, good. What's the value of the acceleration if this coin is at rest? What is it, Kathleen? 0. So m times 0 is 0. So the net force here is 0 because it's at rest. The force of the hill? Now we better find that. Let's say sine 25 degrees is equal to opposite over the hypotenuse, m times g. But m times g is 0.007 kilograms. Got to go kilograms, right? Times 9.81. Let's get FH there. I get 0.02902. All right, so FH, I'm going to make it a negative number, negative 0.02902 newtons. Let's take it over to the other side. The force of static friction is simply going to be equal to positive 0.029 newtons. Does it make sense that static friction would be equal to the force of the hill here? If it isn't moving, the force down the hill has to be equal to the force up the hill. They have to balance. And then, of course, that force down the hill, FH, is really just a normal force and the force of gravity combined already. Let's take a look at these two problems now, please, at your desks. You right now? All right, everyone, taking a look at number 2, it says, a loonie of mass 7 grams is placed on the surface of a rough book. And it's on an incline. Okay, so this is what it essentially looks like. We don't have an angle here. We're trying to find the angle. It's a little bit different than the other questions because we're trying to solve for a different variable than we're used to trying to solve for. Here's the loonie. It has a mass of 7 grams or 0.0070 kilograms. It's just 7 divided by 1,000. There is a force of static friction that's acting up the hill. The maximum force of static friction is 4.40 times 10 to the negative 2 newtons. And there is a force of the hill pulling it down. But we don't know much about the force of the hill other than the force of the hill must be what value? It's got to be equal to static friction, right? If it's not moving, the force up the hill has to be equal to the force down the hill. So it's going to be 4.40 times 10 to the negative 2 newtons. In all the other questions, we had to calculate the force of the hill. This time we have it. Now, we are going to do something with that, though. We're going to say the force of gravity acts down, and the normal force acts perpendicular to the surface, Fn. Okay, the force of the hill, right here, is going to be the combined normal force and gravity, and it's going to be at 90 degrees to the normal force. Okay, we want to find the angle. This time we have FH. We normally say that sine theta, not 30, sine theta is equal to opposite, that's FH, over hypotenuse, that's m times g, 0.00700 kilograms times 9.81. But look, we know the force of the hill. Okay, instead of solving for the force of the hill given the angle, we've got the force of the hill. It's 4.40 times 10 to the negative 2. So to find theta, we're going to take the inverse sine, second function sine, of what you see on the right-hand side there, 4.40 times 10 to the minus 2, over 0.007 times 9.81. We calculate that. We get that angle on our calculators. And literally all we're going to do is say inverse sine, second function sine, use some brackets. Okay, we end up getting 39.8 degrees. Did anybody set it up like that, but yet not get the right answer? Yes? Did you figure it out, or are you still having trouble with that? You did figure it out? Okay. If anybody's having trouble with getting that into the calculator, let me know and I can give you a hand with that. All right, I'm going to give you guys a question right now to do for homework over the weekend, as best as you can. Don't bother copying this down because I've photocopied it for you. But I want to draw it out so that you can kind of see the progression of the question before I hand it out to you, okay? We've got a hill. Okay, that's okay. You guys know how to deal with that, right? 30 degrees. We've got a mass of 500 kilograms right here. We have, we have a pulley going over top of the hill. We have, wait a second, makes it even worse. We have a coefficient of static friction of 0.20 and a coefficient of kinetic friction of 0.10. So we don't even know if this thing moves. If it doesn't move, it's static friction. If it does move, it's kinetic friction, right? Make sense? That sounds pretty hard, eh? Well, let's put a guy inside this box. Let's make it an elevator. Let's say the mass of the guy is 50 kilograms. Let's say the mass of the box, the elevator, is 80 kilograms. Let's say that the system is released and it travels for 4 seconds. So odds are it's going to be kinetic friction because odds are it's going to move, right? 4 seconds after we release the system, the guy takes this ball in his hand and he throws it like this. 4 seconds after the system is released. Here's your question. How far does the ball go? Got it? That seems kind of challenging, hey? Who's up for a good challenge this weekend? Well, all of you are going to get to try it. Do what you can with this, guys. Okay, I understand that most of you will not get this question correct. That's okay. You'd never see a question this difficult on a test. Never. Okay? It's a tough question. But listen, when we go through questions like this, when we try questions like this, okay, we expand our mind. We get smarter when we try questions like this. Then when we do other questions like we've been doing over the last couple of days, all of a sudden they seem so ridiculously easy because we've expanded our mind to deal with questions like this. I'll tell you what, it's a hard question any way you look at it. But it's actually not as bad as it seems. You've just got to break it down into manageable parts, right? There's an inclined plane. You know how to deal with that. There's static friction, kinetic friction. You know how to deal with that. There's a pulley. You know how to deal with that. There's an elevator. You know how to deal with that. There's projectile motion. You know how to deal with that. Deal with all those things separately, and it's not as bad as it might seem. Still bad, just not as bad as it might seem. All right, that's your only homework over the weekend, is to give that question a try.